Hello and welcome to Aerospace and Mechanical Engineering Lab 2. Today we are going to discuss the second lab of Lab 2 series, which is Heat Transfer Lab. Heat Transfer Lab has two parts. One is dedicated to measuring the conductivity of a sample through a linear conduction experiment, and the other one is measuring the efficacy, investigating the efficacy of the lumped capacitance method using a force versus free convection heat transfer experiment. So we're going to start with the first one. For the first one, linear conduction heat transfer experiment, we need to let the experiment run for 20-30 minutes so it can reach the steady state conditions. So we're going to start the first one, which is right here, and then we're going to move to the second one, free and forced convection, so we can have that 20-30 minute leg room between starting this experiment and recording data from it. So the first thing you want to do for the linear conduction heat transfer experiment is to make sure you have turned on the cooling and heating of the sample. So this is where our sample is. This white plastic you see around the sample is actually the insulation. The reason we have this white plastic is because we wanted to make sure that there is no heat transfer other than the heat that is being transferred from the top to the bottom. So the sides do not have any heat transfer, are perfectly insulated. That's how we simulate the one-dimensional conduction, right? And in the middle of this insulation, we have our sample. This is the sample. This is a brass material, and the rest of this device is also made from brass. As you can see here, we have installed thermocouples, 2 on the sample itself and 3 other on the rest of the device, 3 on top here. So 8 total thermocouples. And you want to make sure this is actually closed from both sides. So we have 8 thermocouples installed on the metal itself. And we are going to simulate, I'm sorry, I need to fix this. We are going to simulate one-dimensional linear conduction heat transfer. Again, the first thing you want to do is to turn on the cooling by just turning on the faucet right here and turn on the heating. Okay. So the goal is to measure these 8 temperatures with respect to time. I'm going to turn this off because this actually starts the experiment, and we want to make sure we record the temperature information as much as possible. So the thing we want to do is to apply some heat, measure the temperatures, and use the Fourier's law of conduction, which says Q is equal to Ka delta T divided by delta X, to find the conductivity of the brass. And we have 8 temperature measurements, meaning that we can have 7 different conductivity calculations, and we can do a statistical analysis as well. So we understand how the heating works. We also understand how the cooling works. We need to understand how the temperature measurement is done. It's done through a thermocouple and a DAQ system and a DAQ AMI software. So what I'm going to do is we are going to make sure that the software is set up correctly, and then we are going to turn on the experiment, and you are going to see how the temperature changes with respect to time. So we're going to start with the manual configuration. As I said, the manual configuration is there for you. You can use one of the previously configured cases, but I want to make sure that you actually know how to do this. You go to manual configuration. The first thing you want to do is to add the thermocouples that are connected to this computer using a USB port. So I'm going to double click on this. It will take me to the DAQ device that is connected. The most important part of this is making sure you actually select all of the active channels. We have 8 thermocouples, meaning that we need to have 8 active channels. The sample rate you can change if you want to, but you don't need to change it. And we are essentially reading data off of the active channels. Next thing is to add a display. So we want to see a graph. So this is a display we want to add. It will take a minute for it to actually, for the display to show up here. Yep. We could have done the double click, or we could have just drag and drop. You have to select all of the channels and then drag all of them onto this display. And as soon as I hit run, we can start seeing the temperature readings from the channels. And it does auto scale. As you can see here, the temperature that we are reading is 21 to 21. So the system has cooled down a little bit. It is ready for us to start the experiment. What I'm going to do is I'm going to zoom out of this whole system on the x-axis, so we can actually monitor whether the temperatures have stabilized. How much you zoom out doesn't really matter, as long as you have a good understanding of how the temperature stabilization has happened. If you don't know when the steady state condition happens, you definitely need to go back and watch the lecture recordings. We can either start by logging the data or run without logging data. I'm going to start by logging the data. So, and the next step would be to turning on the heating and the cooling, which we already have discussed. And you have to let this go for at least 30 minutes. So we are going to just let this go as I said. And we're going to come back later to this to check out whether the steady state conditions have been achieved or not. Before moving on to the second experiment, I want to make sure that you actually understand how this power supply works. We have our own temperature probes on the power supply itself, but we are using an external DAC for this. We could have used this as well. And essentially turning on and turning this off is pretty simple. There's a button right here. And we have two displays. The temperature display gives us nonsensical data points. The reason is these probes are not connected, right? So you want to make sure you understand that this don't mean anything. But this display is the most important display that we have. This is essentially the amount of voltage that this power supply is giving out. We can also change this to current, right? And to find the total heat rate that is passing through this whole system, we of course need to find the electrical power that is passing through that can be calculated by multiplying voltage and current. So total power, the total heat flow through this whole system is 10 multiplied by 0.99, 10.4 multiplied by 0.99. So at this point, we know how to measure the temperatures using thermocouples. We know how to calculate the heat flow for our Fourier calculations, Fourier conduction law calculations. The other thing we need to make sure you do measure before leaving the lab is the distance, is the vertical distance between the two thermocouples. It's very important. Vertical distance, right, between each thermocouple, not just two of them. So you have to measure all of these distances on all of the 8 thermocouples, and you have to measure the cross-sectional area. This is a different sample. This is an aluminum sample. We don't really use this sample for our experiments. We have a brass sample already installed, but the cross-sectional area is the same. So for your calculations, you need this cross-sectional area, this part of it that has that is a bit higher than the rest of this, and also the distance between all of the thermocouples. I think we are ready to go to the next part B of the heat transfer lab. So part B of the heat transfer experiment is the forced versus free convection. Your goal in this experiment would be to calculate the heat transfer coefficient of air that is essentially cooling down a heated copper block. And we are going to give you a heater. This is a water heater to heat up water in it. And you will be given 2 copper blocks that are already installed to a thermocouple. You want to make sure that these copper blocks do not have any exposed wires, and these two do not. And you also want to make sure that these connections are not loose, are firm in place. So the idea would be for you to heat up these 2 copper blocks using this water heater, and put one here when the temperature of the blocks reaches 80 degrees Celsius, and put one here in front of the fan and turn on the fan, and then monitor the temperature drop versus time using using the DAQ and the computer that you're given. So the first thing I'm going to do is make sure that this water heater is plugged in. And I'm going to set this to high. And I'm going to put these copper blocks inside. Okay. And we are ready for this to be heated up completely up to 80 degrees Celsius. My next step would be to set up the temperature monitor that we have. Of course, you can use the LabVIEW software that we did talk about a little bit in Lab 1 and also in the first lab of Lab 2 series. Or if you're using an older version of LabVIEW, it usually comes with a software called Signal Express that automates a lot of things for you. So for this specific lab, since you already know how to build a code for LabVIEW, we are going to use Signal Express. And if you're using a laptop that has Signal Express, you are welcome to use Signal Express instead of LabVIEW itself. That will make your job easier. Okay, so we are ready to set up the temperature reading software for these thermocouples and the copper blocks. I'm going to open the National Instruments Signal Express software. We want to open an empty Signal Express project. And here, the goal would be to add a step. We are acquiring signal. It is through a DAQ device. It is an analog input. It is temperature. And the temperature we are using, the temperature measurement device we are using is a thermocouple. Okay, so, and my specific thermocouple is installed on channel 1. You already know how to find the numbering for the channels, so make sure to choose the correct channel. There is nothing else we need to change in this setup. We can just start running the software to make sure we actually have the temperature readings. I did change the data representation from table to tabular to chart to make sure I can progress the changes of temperature real time. When I hit run, you're going to see the temperature is already at 80 degrees. And I'm going to turn off the water heater now. And the next step would be to put this in front of a forced convection system first, and then in front of a free convection system second. Okay, so the forced convection part of the setup starts now. I'm going to turn the fan on. I'm going to hit record, and there's a record button. You can just hit record on my software. And we want to mention that we are recording the thermocouple measurements. So the software is running. I'm going to take this out. You want to make sure you understand that this is hot. And I'm going to put this in front of my fan. The real-time temperature, I'm looking at the real-time temperature right now. It is going down. It's going down very fast. It's a forced convection. We are at 70 degrees now. You want to make sure this actually cools down up to 50 degrees Celsius. Doesn't have to be 50 degrees Celsius, but it is better to go down until you reach the 50 degrees Celsius to make sure you have enough data points. Right now we are at 65. I'm going to wait until my system reaches 60. I'm not sure if I don't think you're seeing this, but we have the temperature real time. Let me put this in front of the camera. This is the real time temperature changes. I don't think you can read the number, but we have already reached 60 degrees. I'm going to stop this, and this is the record button I mentioned. I'm going to stop the recording first. And then I'm going to take this heated thermocouple, put it back in the water heater to make sure it heats up for the next round of the experiment, which is free convection. I can actually turn off the fan and remove it as well. Let's actually see the recorded data. If you come to logs here, the recorded data for the thermocouple, this is for the forced convection, is right here, going from 82 to 58 or 60 in that ballpark. This is your forced convection data. You can change the, you can record this or change the name if you want to. You can export it to Excel. Let me actually show this to you. You can export this to Excel, or you can export it as a text file. Doesn't really matter. If you do export it to Excel, you want to make sure you actually sign into the Microsoft Excel that is already on this, installed on this machine. So it needs you to sign in. But if you do not sign in, you will lose your data. This is essentially the type of data you will get. It will give you the time and everything, and then it will give you a lot of temperature readings and time reading as well. I am going to close Excel. So we are done with the forced convection part. Next thing is the free convection. Right now we only have one thermocouple. That's why we actually have to do this experiment twice. I'm going to move this computer away. I'm going to turn the heater on, and we are still monitoring the temperature. We are not recording any data. We are just monitoring the temperature. I'm going to put this back in the heater. As soon as I put it back in the heater, temperature starts going up. Right now, we are at 68 degrees. So you want to make sure you actually wait for it to reach 80 degrees. I'm going to leave the computer in front of the camera to make sure you actually see what is going on. We are at 75, close to 80. I'm going to stop the heating process again and take this out, this time without any fan. Okay, and then we are going to hit record again. It's asking us to choose a thermocouple. It's already selected. We can actually name this. I'm going to name this free. Then hit record. You can see the temperature is dropping at a slower pace this time around, which makes sense because we don't really have a fan in front of it. So we just have to wait a couple minutes. But in the interest of time, though, I'm going to stop this part of the experiment right now. And so essentially, when you see the temperature goes down to 50 degrees for this as well, you are ready to stop the experiment. I'm going to stop the experiment sooner. So I'm going to hit the record button again and hit stop. And down here, you see we have a free, we have a forced recording. The free recording, you have the temperature. Again, export to Excel. Just have to make sure you remember to sign into Excel. And we have the forced measurements. Forced convection, free convection measurement. We have both of them. You just have to take this home and use the equation that is provided to you in the slides to calculate the heat transfer coefficient. Okay, so it looks like we have reached a steady state condition for our linear conduction experiment. I'm going to zoom out a little bit so you can actually see the changes. The temperature change is obvious here, but it has plateaued, meaning that this is the temperature data we can actually use. So what I'm going to do is I'm going to stop the data acquisition, and it is asking me how to export this file. We don't really need to change any of these options. It has exported the file in a CSV format. We can also come here and export the data again. Right here, see user linear conduction desktop. We can just hit export, and we can use the exported data right here. Is the temperature measurement from each of these thermocouples. So the temperature that I want to use is the last one for your conductivity measurements. But at the same time, I want you to actually draw this graph for me in your lab report. So at this point, we are done with the linear conduction experiment. We are also done with the force versus free convection experiment. And we are ready to go home. Thank you for watching, and see you next week.